portfolio. So Martin, the floor is yours.
I'm afraid you have me again here. Apologies for that. It's really not my presentation. It's made by Simon O'Brien, who was subsurface manager of the Quest facility in Canada. For some reason, he resisted the opportunity to come to Venice and came to me to stand and present his slides. So yeah, I'll be talking about MMV performance at the Quest facility. And nothing changed, maybe even more emphasis on really do not use what I say for any investment decisions because, yeah, obvious reasons. So the Quest. Quest is a facility that captures CO2 from hydrogen production. Hydrogen is produced from natural gas and is used in production of synthetic fuel. So hydrogen is used in the early phase, and CO2 is scrubbed and it's compressed to about 10 megapascals, and it's in dense phase throughout the system. So it's being dehydrated to minimize the water before it's injected. And it's taken through a 65-kilometer pipeline to basically the injection sites. I'll talk a little bit more about the sandstone reservoir, which is at approximately 2-kilometer depth. And yeah, the facility has been injecting for 8 years now at about 1 megaton per year into 3 wells. So the facility is operated or has been operated by Shell. Yeah, so the target is basal Cambrian sandstone. It's a deep saline aquifer, about 2 kilometers, as I said. Very good porosity and excellent permeability. You can see in this picture that there are additional aquifers, shallower ones, but those are shared with hydrocarbon production, and that was the main reason really why going deeper into something that is less penetrated, has less sort of competition for space, for pressure, and is also less risky from containment point of view. Storage complex, several seals, it's generally speaking very safe, extremely secure, right? It has 2 salt evaporating sequences and also very thick Cambrian shale just above the sand, the reservoir. So 3 well paths, each containing 1 injection well and 1 deep monitoring well. Yeah, and each side has, and altogether there are about each pad has between 2 and 5 shallow groundwater wells as well. Conventional drilling methods, yeah, multiple steel casings, 3 in freshwater zone, all cemented to surface, and a comprehensive MMV program that was established prior to start of injection in 2015. You can see in this map or aerial photo, the distance between the ejection sites is about 6 kilometers between the 3 pads. Now, this is the MMV plan for Quest in 2015, so pre-injection. You can see it's quite a lot of it, right? It's recognized. It was recognized back then. It was first of a kind, so quite a conservative approach, right? It was covering everything from atmosphere to geosphere, as we always think about these days. But it was site-specific. It was based on risk and risk assessment of the site, and it was independently reviewed before it was really permitted. It's a combination of new and traditional technologies, and yeah, had baseline data collected before startup. Maybe, something of interest, probably the most costly thing is for the seismic plan, right? So there was a plan for time-lapse walkaway VSPs, but also for repeat of 3D seismic survey in, every few years, really, several times during the injection and post-injection as well. That was the plan. Now, some technologies that were, maybe relatively new or, but proved to be useful and interesting. INSAR, right, satellite radar technology, looking at the surface deformation. Generally, subsidence observed in the whole area. I think it's related to production in the area of hydrocarbons. And compared to models, only about 1/3 of estimated deformation was observed. And it was concluded that it was unlikely to see effects for years, really. So the recommendation was made, or the plan was slightly updated in terms that even if the data is acquired, but it is not processed and analyzed continuously until there is some reason to do it, right? So it was kind of made contingent on perhaps some other monitoring technologies. Now, post-start of injection, it was a reassessment of the risks, bow tie analysis again, and this quite large bow tie that you can see here related to different types of leakage risks was collapsed quite significantly, right? Because a lot of these threads were related or were addressed already in site selection, and only a limited number was really kind of would really influence or impact any decisions in the operational phase. And it was also very important or useful to distinguish between passive safeguards and active safeguards, right? So passive ones are those that are always present or that are in place. They may fail, they may not, but active ones are those that would only be present if there is a decision to intervene, if there is a trigger that, based on monitoring information. So by 2020, there was an updated MMV plan. And as you can see, it's quite a lot simpler, right? So there was a lot of reduction and elimination of technologies that really, as I said, did not drive decisions. Updated, reflected the updated bow tie, and really focusing on improvement in efficiency and effectiveness and cost reduction. And one of the key things was really the optimized frequency of monitoring. Few things, like several, most of technology was tested or, what was run for a certain amount of time after the start of injection. And then a decision was made whether it's worth continuing or whether it should really be just a trigger or whether we should reduce the frequency. Again, one of the most notable one is basically getting rid of the idea of the need for repeated 3D seismic survey. Okay? So that was the most important kind of cost reduction. And that was not something that was really contested because there was VSP data available. I'll show you a little bit more of that. It shows conformance to predicted models, and there was a mutual agreement between the regulator and Shell and operator that basically it's an overkill, and there's no much point to do that every few years, essentially. A few other things, there was, for example, a sampling of groundwater wells with individual landowners, which was really started very good sort of stakeholder engagement. It was a good basis for it, but in the end, it was really kind of almost a push from landowners to stop it. There was they felt like there was no more need to do that, after the initial baseline was acquired. Another important thing that was done was adopting a tiered approach, right? So really kind of grouping the technologies into 3 tiers, and one of them was really focusing on downhole instruments that are continuously monitored. Second tier, the near wellbore technologies that are periodically monitored, and tier 3 technologies that are typically only monitored or analyzed if there is a trigger from tier 1 or 2 that something is maybe out of ordinary and needs special attention. So let me just illustrate a couple of these. So tier 1, critical MMV technology, but not really something unconventional. It's tubing head and annular pressure monitoring, production casing. The annulus contains drill cell with a nitrogen cushion above, and basically as long as there's a stable pressure and drill cell levels, it confirms annual integrity, right? So there's something that is continuous. Microseismic data, so that is something which is regular, and it was based on, first there was a baseline in 2014, no locatable events detected in the baseline period. First started 9 months after start of injection. Activity increased in 2017, roughly 2 events per week. But all events located below reservoir in the basement, some transfer into the basement, but magnitude was very low, so about 0.7 on average. So the conclusion is that there is no risk to containment, essentially. Groundwater monitoring, I mentioned. Extensive sampling, baseline survey, over 200 wells, really winning the trust of the stakeholders, establishing that sort of engagement, communication. But in the end, it was really put on hold. It was felt like the groundwater wells on the injection sites, which are continuously recording, would detect the CO2 leak very easily or very quickly as an abrupt drop in pH, yeah, and that would trigger some other response. Something else to mention: microseismic technology trial. This is kind of again an attempt to reduce cost, looking at the dust fiber application together with surface nodes. As a reliable, effective seismic monitoring tool. So surface node stations were deployed within 10 kilometers radius around Quest well sites. And 3 new data sets were collected, processed, and compared to downhole geophone data, right? And there is this plot over there where you can see very good sort of overlay. And I think, I don't know if the final conclusion is out there, but it looks like a good match, and generally something that we can go ahead with as a technology to use. Yeah, this is time-lapse VSP that I mentioned before. Baseline, pre-injection, then 4 more repeats. And you can see, 2 different processings of the VSP lines, and kind of interpolation of the results in any kind of map view. Again, actually very well behaved plume, and again, something that was pretty much matching what was expected. So no real surprise, and therefore really the reduction into need for a repeat 3D survey. And also any kind of reduction in VSP frequency. So, in conclusion, Quest was first of a kind in Canada and overall as a kind of commercial injection facility, and the early focus was on demonstrating that CCS will work, and also looking at it. Evaluating and testing technological limits and what would be useful. Consciously, there was a conservative approach to risk, even if it was assumed that geological risk is extremely low. But it was this dialogue, and I think it's really important to stress that it's not something that was basically pushed from the operator side or regulator side. It was a very good dialogue, and both sides were kind of developing the regulation and those requirements as the project was progressing, and you know, that is, I think, the key to success and to performance over there. And in terms of approach to MMV, its well risks are primarily managed by conventional well integrity management systems, and many of the activities or application of technology is contingent on the outcome of these ones. And yeah, I guess the biggest issues are operational, how to fit the new technologies in the surveillance system, what's the most effective, frequency, but the main thing is continuous improvement, right? And that's what we're trying to achieve. Yeah, thank you for your attention. And if you have very difficult questions, I'll try to avoid them, right? But or I'll improvise. Thank you.